Good evening and good morning to some of you who are joining us from APAC. Welcome to the Bay Area Ray Meetup of the new year. Happy New Year and belated happy, healthy New Year to all of you. Welcome to our first meetup. We are really super excited to get this going. This is our first meetup after 2 years of absence because of COVID, and we're looking forward to get this cadence going on a regular basis. Now, if you are using Ray, and if you're actually using Ray to solve some of the problems, or you're scaling Ray to use your machine learning workloads, and you want to share that with the community, please get in contact with us. It would be great to actually have you share or give a talk or write a blog about it, because we believe that it is you who is going to actually help us get going. As you will hear from Robert very shortly, that community is our core. It is the catalyst that drives our adoption. And as you all know, all successful projects in the past have relied on the support and the thriving community. And we are relying on your support, and you can rely on us to make sure that you are successful in the adoption of Ray. And so we're counting you to spread and shine the ray of light. Having said that, enough of evangelism. A few housekeeping items. All your mics are muted right now. We can't hear you, nor can we see you, unfortunately, but hopefully that might change in the future. If you're having any Zoom difficulties, put something in the chat so we can actually coordinate with you. But enter all your Q&A during the Q&A section in the Zoom panel for the Q&A, because it's easier for us to navigate through than to scroll up and down the chat. And while you're doing that, you might want to just say hello to everyone who is actually on the meetup. Tell us where you're hailing from. You know, we really want to know. I know we actually have a global audience today, so we'd love to hear where you're dialing in from, where you're hailing in from. You can actually use that chat. And having said that, we actually have a tight agenda today. So we're going to go to our next slide. We have a tight agenda today. Robert, can you move to the next slide? You're going to hear first from our fearless leader, who is the co-founder of Anyscale and also the co-creator of Ray, Robert Nishihara, who's going to reflect on the state of Ray in the last year or so. And then we'll hear from Zhe Zhang, who's going to give us the idea of where Ray is today and what do you expect coming in the near future. And then we'll dive into the Ray Datasets, which is the experimental new library built on top of Ray that will take us until about 7-ish or so. And then we'll hear from the community. We'll hear from Patrick Ems about how they're actually using Ray and how they actually build a scalable data catalog. With that said, it's my honor and pleasure really to introduce our co-founder at Anyscale, Robert Nishihara. He's also the co-founder and the co-creator of Ray. And all of you guys over here, say hello to the community.
Thanks so much. And yeah.
All right. So we're going to have you take over, Robert.
Cool.
I'm going to mute myself.
Awesome. Well, thank you everyone for joining us here. I'm going to say a bit about Ray in 2021, and Joe will talk more about what's ahead in 2022. But 2021 was really a huge year for Ray, and I'd love to just touch on some of the things that have been happening in the community. So throughout the year, we've seen tremendous growth in the community. That's developers, companies, some longtime contributors, as well as a ton of new people contributing back to the open source project and really helping to create a great project. That's been everything from ironing out a lot of the rough edges, building new libraries, improving core usability and polish and performance. And this is something we really aspire to repeat in the coming year, together with the Ray community. So thank you so much for attending today and really, being part of this meetup group and helping build a great project. So to put some numbers on that, we have almost, at the end of this year, we have almost 600 contributors. That's roughly 3x increase. We're continuing to see more and more companies building internal teams, to invest in Ray, to build on top of Ray, to develop libraries on top of Ray. And these are some of the statistics that we look at as, a sign of a healthy community. Another one is that in 2021, we released 14 Ray releases. And these are, many of these are really significant releases, often with major improvements. Just as one example, and Joe will talk more about this, but in 1.10, Windows support has reached another level of maturity. It's now in beta. So we're super eager to learn about your experience using Ray on Windows. And there are many other things like that that have been coming out recently and that are just step changes in quality. Another exciting number, we've reached over 10,000 commits on Ray. So on the Ray project, that's just a tremendous amount of software engineering effort and development has gone into building building this project. We also have several thousand, over 3,500 Slack members, and that's one of the areas where our the Ray community has been coalescing, engaging with each other, helping each other out, talking about use cases, talking about development plans, and that's one of the vibrant places that people gather. Another thing, one of the things I want to talk about a little bit, which is one of the things that really makes Ray special and where we've seen a lot of growth, is the library ecosystem. And 2021 has been a big year for the Ray ecosystem. So just as a reminder of how everything ties together, how the Ray ecosystem ties together, Ray overall, right? Ray is a universal framework for distributed computing. It's super general, right? You can use Ray for scaling essentially any workload. And that generality, that level of generality is critical for supporting this rich library ecosystem on top. That's everything from training, deep learning, production serving, data processing, stream processing, anything you can imagine on top of Ray. And of course, by running these libraries on top of Ray, the whole point of that is not just that you can use these libraries individually, but rather that you can use them all together and build applications that do all of these things together, right? So if that you can build single coherent applications that load your data, that feed it into training, that do hyperparameter tuning, that deploy the model, and all of these things. And this whole ecosystem is really something that that excites us and that we think is special about Ray. And of course, if you use Ray, or if you use Ray directly, or you use a library on top of Ray, one of the advantages of that is that you can then run your application anywhere, right? You can run your application on any cloud provider. You can run it on Kubernetes, on your laptop. You can run it on Anyscale, which is our managed Ray service. And so each of the components, every time there's a new addition or an improvement to the ecosystem, to one of the libraries that's part of this ecosystem, that adds value. That is a benefit for other users of other components of the ecosystem because everything works together. So a natural question is just what's new with the ecosystem? What happened in 2021? And throughout the past year, and of course, continuing into 2022, there's just been a ton of investment and effort in really ensuring that the best libraries for machine learning all run on top of Ray, and that Ray is the best way to scale these different libraries. To give you a couple examples, so XGBoost is one example. There are talks online, you can on YouTube, you can hear about how Uber and others have sped up training by 5x just by deploying XGBoost on top of Ray, using the XGBoost Ray integration. That's sort of one success story there. And XGBoost, of course, is super popular for training machine learning models. Horovod is another example. In fact, companies like Uber have deployed Horovod on top of Ray, and that's allowed them, because they can also deploy XGBoost on Ray, that's allowed them to really consolidate their deep learning and traditional machine learning tech stacks. And of course, by deploying on top of Ray, all these libraries, they immediately leverage Ray's elasticity, right? The auto scaling, the hyperparameter tuning. And because of that, these kinds of data points, that's how Ray is helping to bring this common infrastructure to the production ML ecosystem. So XGBoost and Horovod are a couple examples. Another example is Dask. And actually, so Dask has a great library for data processing. And there are people at Amazon who've managed to, and others who have managed to speed up important Dask workloads by around an order of magnitude by deploying Dask on top of Ray. And we've heard stories where people are able to take important workloads and scale them to clusters that were 7 times larger and really cut the end-to-end cost by 3x. And in fact, in one story that in one case study, doing that saved something like $500,000 per job. So these are, very large scale workloads, and and as part of this ecosystem, Ray can be a great way to scale these kinds of workloads. But of course, we're talking about individual libraries, but the real benefit of Ray here is that these libraries don't exist in isolation, right? You're not just using one library and then you're done, but really they can be used seamlessly together in a common application. And with all of these examples, we've seen that Ray is really becoming the tool of choice for scaling machine learning workloads, scaling machine learning libraries, and really building these kinds of distributed applications. So that's a little bit about the ecosystem and about libraries. But beyond the ecosystem, in 2021, we've seen Ray being used for a huge variety of applications, just far beyond where we were 1 year ago. And actually, one of the biggest shifts is a focus on online production use cases. So there's a super broad user base. All of these companies here presented at our previous Ray Summit. That was in 2021. And by the way, we're going to have another Ray Summit this year, so hopefully we'll be in person. But all of these use cases are, the use cases are quite broad. And you can imagine all of these companies, their talks online on YouTube. You can check them out about how they're using Ray. But it's really everything from building scalable infrastructure for financial services to optimizing recommendations, recommending in-app purchases, large-scale machine learning on aerial imagery, building machine learning platforms, and many more things. And to give you just a couple examples, this is a picture from the talk that McKinsey gave. So McKinsey and Quantum Black partnered with the Emirates Team New Zealand and designed this boat, this boat in this picture, using Ray to do reinforcement learning. And they gave a talk about this at the summit, but basically using this boat that they designed with Ray, they won the America's Cup, which is the top competition in sailing, which is just incredible. It's really, quite inspirational to see these kinds of use cases of Ray in the physical world. Another example, completely on the other end of the spectrum, is a company called Dendra Systems using Ray for ecosystem restoration. So their goal as a company is to plant billions and billions and billions of trees. And they're using Ray to do everything. And of course, they have to decide from photographs where to plant the trees. They have to train models that can do the computer vision to understand the images and make these decisions. And they're using Ray for everything from the training, the inference, the computer vision, the testing at a really tremendous scale to plant trees. And it's another example of just the kind of diversity of use cases that we see with Ray. Another data point, Uber and Shopify and others talked about building machine learning platforms on top of Ray. And that's something we increasingly see. A lot of companies around this time are looking around to build their next generation machine learning platforms. And a lot of them are choosing to build on top of Ray. And a big part of that is the library ecosystem. Great scalable libraries for machine learning on top of Ray. The fact that you can use the generality, the fact that you can use all of these libraries together, the extensibility, the ability to scale other libraries on top of Ray, the portability, right? The fact that you can use it with any cloud provider, the fact that you can use it, with any machine learning library or framework. So, building machine learning platforms is another example of an exciting use case that we've been seeing a lot about. So lastly, I just want to, end with this slide and say that there have been, in addition to all of these use cases, these use cases and these are really what excites us. And I know many of you have exciting use cases that you'd probably be interested in sharing. So we will be hosting a Ray Summit in 2022. So, please keep an eye out for that and let us know if you're interested in sharing more about what you're building. But really, want to thank you all so much for making Ray what it is, for pioneering all these use cases, and just helping, building such a rich ecosystem. We really obviously wouldn't be here without the whole community. So there's going to be a big year ahead of us in 2022. Looking forward to an even bigger Ray Summit later this year. And I'll hand off things to Zhe, who's going to talk about what we have lined up for the year ahead.
Thank you, Robert, for the inspirational talk. Next, I think we're going to have Zhe, who's going to give us a talk about where Ray is today and what we're going to see in the upcoming future. So take it away, Zhe.
Thank you, Robert and Jules. First, I'm really excited about us having the meetup again. As Drew mentioned, after a long time, very excited talking and interacting with the community. This part of the talk is about what's new in our latest Ray 1.9 release and beyond. As a brief introduction, I manage open source engineering at Anyscale. I think to simply put it, we have three overall themes to adding improvements to Ray in the 1.9 release and beyond. So basically in the Ray core area, we really focus on reliability and stability at large scale. And then on the library layer, we're trying to build a suite of libraries that's easy to use, higher level, and more suitable for production workloads, to use them to wrap around the very elegant low-level APIs of Ray itself. And then thirdly, we want to improve the deployment. So both deploying a Ray cluster and deploying a code to the cluster to make sure these two types of deployments are simple and clear to understand. So I will start from Ray core. I think attendees to this meetup probably have some basic understanding of Ray's architecture. So this chart is basically a typical Ray cluster. A Ray cluster is a collection of Ray nodes, and there's only one special node in the cluster called head node, and there's only one special component in the head node called global control store. This is the only single point of failure in the entire cluster. So obviously, we want to improve the availability and scalability of these components. So the feature we're working on, which we plan to release in the upcoming 1.11 release, is to make the backend of GCS, Global Control Store, more pluggable. So here is the detail of this work. So as of now, the Global Control Store uses Redis as a storage backend. It has two functionalities. One is to store internal data. There's an internal data table on Redis. The GCS will interact with Redis for this. And then the worker nodes, the relet, will interact with Redis for pub/sub purpose, generic publishing messages and receiving from other relets. So I think both reliability and scalability bottleneck is at Redis, because Redis is a single instance, it's not scalable. If the node crashes, then not only the GCS process, but also the data stored in Redis will be gone. So the first step we take to address the problem is to make the backend pluggable. So different environments can use their highly available key value store. As a secondary benefit, it can also make the message pops up much more scalable. We want to push the scalability limit of a single Ray cluster to be multiple of the current state. So how about outside of the central global control store? We're working on a few pretty exciting efforts. If you're interested, please check the link I added at the bottom of the page. It's a public roadmap for Ray core. I want to emphasize three efforts for the object store and for scheduler. On the object store level, we're working on improving the object lifetime management, again, to handle node failures. We want to make sure the developer has the developers have a very clear contract of what to expect for different kind of failure scenarios. And then the second item is personally, I'm very excited and also interesting connection to the following talk, which is petabyte level of data processing. I believe Patrick's talk will be related to that. On the scheduler level, we're working on an effort that is basically rock solid scheduler logic. I think we all know that one of the key advantage of Ray on architectural level is distributed scheduling. So every relet can make scheduling decisions, but with this special power comes with the complexity. Shortly put, we need to add the scheduling logic in multiple places. And what we're working on now is to consolidate logic so we can better test it, make the code more understandable, and make it easier to add features down the road. So on the library front, I think this is probably even more directly exposed to developers. I want to emphasize four key libraries we're developing and lay out the very rough timeline. We're releasing the libraries at different stages. Of course, in actual execution, there will be, we will revisit the plan release after release, right? So the first library is Dataset. Dataset has been progressing really quickly. The initial prototype, when I was making the slide, I was looking back. I was really surprised. We only started working on it actually last year, June. And at this point, it's already beta released. So I think in 1.11, 1.12, we want to make Dataset GA. And this is very closely related to the talk that Clark and Alex will give. And workflow library currently is alpha stage. We want to make it beta, but this is a library which is more open-ended. So your input will definitely be very valuable. Please talk to Ray team about this. So the retrain library currently is a beta, and we're thinking about a more holistic API design to make the different model machine learning model training libraries more pluggable in this framework. And serve pipeline is for people to serve multiple machine learning models in sample fashion. Currently, it's experimental. We want to make it alpha or beta in the upcoming 1.11, 1.12 release. I want to just give a little more detail of the two libraries, Dataset and workflow. So Dataset, simply put, is both a standard format and a mechanism for different components in Ray to exchange data in a very efficient way, ideally zero copy, right? So by different components, I mean, for example, data processing. People can do Spark on Ray, Dask on Ray, and then model training. People can do TensorFlow on Ray, PyTorch on Ray, and then eventually scoring and maybe even online serving. So if these different components use a dataset, the performance and the developer velocity can be much better. To illustrate this, you can look at the code snippet at the right-hand side. So first, we will load a Parquet file really simply and do arbitrary function on the dataset and shard the file and feed it into different workers of XGBoost. Everything in the coherent vanilla Python script. You can develop unit tests locally and scale to the cluster. The second library, workflow. So workflow, simply put, is for people to use tasks in a more convenient and fault tolerant way. So typically when people use tasks, they want to do multiple things with dependencies among each others. So what workflow allows you to do is to specify the dependencies and handle retries, fault tolerance for upstream tasks. So downstream tasks know exactly what to expect. For example, exactly once delivery. The third area, finally, I want to touch on deployment. On deployment, we really want to make sure it's clear and simple to understand, right? So I want to emphasize three things. One is we want to make Ray client the default option for interactive development, connecting people's laptop to a Ray cluster. And our new offering job submission, we want to make that one the default option for production jobs. After you're happy with the interactive development, you package everything as a production job to submit. And then runtime environment is our offering to manage dependencies and package for the artifact developers will generate. So lastly, so in a more broad sense, right? So we're also enhancing the deployment and language ecosystem a lot. I think Robert already emphasized Windows support there has been a long effort, but now we have reached the beta in 1.10. That will come out. So for people using Windows, we definitely will appreciate the input a lot for you to try it out. And Kubernetes, that's another area we're putting a lot of effort on from the community. There's a community project called KubeRay. It involves engineers from Microsoft, from ByteDance, from Ant Group, and a few other companies. We're actively investigating what's the best way to integrate with KubeRay to run Ray on Kubernetes clusters. And we're also improving our support for Conda, for M1, for Java and C++. Java, C++, I want to really acknowledge the contribution from Ant Group, Ray team. And yeah, that covers this part of the talk. So 1.9 and beyond. Happy to discuss if you have questions.
Well, thank you very much, Zhe, for giving us an update on what's the current state of Ray. It's come a long way. I remember attending this meetup about 2 years ago at San Francisco in Galvanize, and we were still at 0.8 release, and today we're almost close to 1.10, and all these new libraries that have emerged. If you actually want to start learning Ray, here's a slide that you can just get started. Just do pip install and you're there. You can actually go and run with it. We have a copious amount of documentation in each and every library. So go to our docs.ray.io. Please join our meetup. You're already here, so I don't need to acknowledge that. We have forums where we actually talk about all these different native libraries as well as the ecosystem at a very highly technical level. All of our committers and all of our contributors are online to answer your questions. Join us on Slack, follow us on social media. We would love to hear you. Get us in touch with us. And a bribery, give us a star on the GitHub. Now, let me see if you actually have any questions for you guys. Robert or Zhe, this might be something either one of you can actually answer that question. Robert, you mentioned something about in one of your slides in the layered cake of functionality and capabilities of Ray, that it's a general purpose and a universal framework. What is so universal and general about it? Can you expand on that, please?
Yeah, that's a great question. I think one of the things is it really has to do with the choice of the APIs for Ray. And if you think about a lot of different distributed systems, like take Apache Spark, right? Spark introduces this concept of a data set, right, or a data frame. If you think about other things like TensorFlow, it introduces the concept of a neural network, right? And so if you're building applications that are about processing a data set or training a neural network, then those are kind of the right abstractions. On the other hand, if you look at the core Ray system, and I'm not talking about the ecosystem on top of Ray, but just the core Ray system, the API there, the concepts introduced are really just Python functions and Python classes. So the existing concepts that people use when they're programming in Python. And it's just that Ray translates, instead of like introducing new concepts like a data set, what Ray does is it takes the existing concepts that developers are familiar with when they're programming in Python and sort of translates those over to the distributed setting. So you can take Python functions and turn those into Ray tasks and Python classes and turn those into Ray actors. And so a lot of the generality comes from the fact that we are, instead of introducing new concepts that you kind of coerce your application into, we are taking existing concepts that developers use and sort of translating those over to the distributed setting. And so you can really express a very broad set of applications in that way. Now, of course, functions and classes are somewhat lower level than data sets or neural networks. And that's hence the importance of this library ecosystem on top of Ray, because ultimately you want to have great libraries that you can use off the shelf without having to build all the application logic using functions and classes.
Thank you, Robert. That was a great elaborative answer. I think one more question that either Zhao, you or Robert can actually take that. Are there any case studies of interoperability between, say, GC Cloud, ML ecosystem, and the Ray ecosystem? So,
Joe, you might know the answer more than I do. I'm not aware of any case studies, like published case studies like that. I think there are some with people using SageMaker along with Ray. So that, and there might be some similarities there, but that would probably be the closest.
Thanks. Yes, stay tuned, because Shopify, which is a very important open source reuser, they're on GCP, and they will publish how they're using Ray fairly soon.
And I think the last question that we might want to answer before we actually move on to our next speaker, Alex, is there a Spark ecosystem integration with Ray? Probably want to mention something about Spark on Ray, but sure, elaborate on that one.
Yeah, there's a project, RayDP. I will type the link in the chat, and I'm sure Clark and Alex have a lot more insights. So I think for detailed questions about RayDP, we can even further discuss in the next talk. But let me paste the link first.
We'll put the link on the Slack. Well, having said that, I think this is a great context that both of you actually have set with what's happened with the Ray community and how Ray has actually progressed in the last 2 years. And it's actually great to see this momentum going forward. And we depend on you to carry us to the next level. And I think next thing we want to talk about is transitioning into the new native libraries called Ray Datasets that is currently in beta. And we have Alex and Clark, both who are software engineers who work on the Ray dataset. They're both committers and contributors to this massive project. So I'll have them give you an introduction of what Ray Datasets is all about. And you can ask them more questions about everything you want to know about Ray Datasets. So take it away, Alex, you're on.
Yeah, thanks, Jules, and thanks, Robert and Zhe, for that great recap of where Ray has been in the last year and where it's going. It's crazy to think how quickly all of these projects have been growing. So as Jules said, I'm Alex. I'm a software engineer here at Anyscale and a contributor to Ray. And Clark, do you want to just really quickly introduce yourself too?
Yeah, sure. Hello, I'm Clark. I am also a software engineer at Anyscale and also a contributor to Ray, and I like working on data stuff.
Yeah, thank you. Yeah, and we're going to be talking today about essentially like unifying how people are currently doing their data pre-processing and training, specifically on Ray using datasets, which as Robert and Zhe have alluded to, has been something that's really gained a lot of traction in the last couple of months, and hopefully will continue to gain traction. All right, so we're going to get started today by essentially taking a look at how people are currently doing ML training and scoring and how they're setting up these pipelines today without Ray datasets. And we're going to really use that and the challenges that people are facing today to essentially motivate why we built Ray datasets to begin with. Then we're going to take a look at Ray datasets, obviously, which is what this talk is about. And then finally, we don't want to just tell you the theory of Ray datasets. We want to spend a lot of time showing you guys essentially how people are using datasets today and the early results that we're already seeing people get. Okay, so with that, let's take a look at what a typical data processing pipeline looks like today. So this may look familiar to many of you, even many of you who may be only using a single component of Ray right now. So typically, the way people do their training pipelines is they'll start by using some kind of a data processing framework to do their pre-processing. So if you have a lot of really big data, Spark is typically the go-to framework for doing this. For those of you who really love the Python ecosystem and want to stay within it, Dask is probably by far one of the most popular distributed data frame libraries in Python. So typically people will use these types of frameworks to do their data pre-processing. But they don't have an easy way of feeding that data into their training frameworks, which are almost always written in Python and are almost always use slightly incompatible dataset formats. So typically the way people deal with this is they'll first checkpoint their data by writing it into some storage like HDFS or S3, and then pick it up in a new job and use Horvath or XGBoost or whatever their favorite training library is to train. And finally, because you have multiple components in multiple jobs that depend on each other here, you'll need to wrap that around some kind of an orchestrator or a workflow engine like Kubeflow or Airflow. And because a lot of these frameworks were written in different languages, you either need to mess with a lot of YAML files or you need to find some way of orchestrating like a job that uses multiple languages and multiple different clusters. Okay, so let's take a look at some of the concrete challenges that people face when they're doing this. Really, there are a lot of inefficiencies in the way people are currently doing their setting up their data pipelines or their ML training pipelines. So one of the big performance issues here is just that this is a very inefficient process. So a lot of Python frameworks suffer from the global interpreter lock, and in order to get around that, they find themselves constantly serializing and deserializing data in order to pass it around between processes. Within the Java ecosystem, you may not have a global interpreter lock, but people still in practice end up finding that when it comes to passing data between nodes, they're doing a lot of serialization and deserialization that really isn't fundamentally important to their job. And finally, if you're writing data to storage, that almost requires you to serialize it or maybe compress your data into some other format. And then there's a lot of complexity in both implementing and like operating these types of jobs. So if you're using Spark, you have a lot of cross-language difficulties between Java and Python. Those two ecosystems don't work well together most of the times. You also typically find that you'll have things like your pre-processing typically uses CPUs, whereas your training uses GPUs. And so you need a cluster that's able to efficiently and like intelligently schedule your tasks, your CPU tasks on CPU nodes and your GPU tasks on GPU nodes in order to be really, really efficient. And then finally, there are some operations that people in the like ML research community have discovered and realized they really like on single nodes, but there's currently no good way of doing them efficiently in a production setting. Okay, so as you may have imagined, these challenges are essentially why we built Ray datasets. So now we're going to take a look at Ray datasets and how we believe that Ray datasets can help solve these problems. So as a very brief intro to Ray datasets, essentially Ray datasets provides you with a distributed table abstraction, and it's built on top of Ray. And so we'll see really quickly just how like Ray datasets leverages Ray and what features it uses. So as I mentioned before, Ray solves a lot of these problems that we've mentioned. So for example, it has an extremely efficient data layer. We've spent years now, really working through the kinks of making sure this thing is really, really efficient. And so we can solve it already solves a lot of serialization problems by doing zero copy reads and having shared memory. The Ray scheduler handles a lot of really intelligent things to schedule your tasks, and it can take into account things like GPU tasks. And finally, it provides a very general set of robust primitives, which means that it's easy to, it provides you with the ability to do very complex things and run other special frameworks on top of it. Okay, so now let's take a look at datasets. So datasets is essentially a distributed dataset abstraction that's meant to unify both the concept of a dataset in the data frame pre-processing sense, as well as the dataset concept that distributed training frameworks have. And so datasets is really meant to do three key things. So first of all, datasets is meant to be a universal way of essentially getting your data from wherever it currently is and into a Ray cluster where you can work with it more easily. The most important thing that people usually want to do with datasets is do a little bit of last mile pre-processing with that data so that they can feed it into a training framework. There's a lot of like little things in the last second pre-processing that you may want to do that don't make sense to checkpoint. And then finally, another really important use for datasets is being able to do parallel computation that uses both the GPUs and CPUs. All right, so one thing to be really clear about here before we dive into it is that datasets is not meant to replace Spark or the other really common data frame libraries out there. We think those libraries do a really, really great job at what they do, and we don't want to replace them. We just want to make sure that they work
Alex,
better.
I think your sound cut out.
Oh, I'm sorry.
Assuming it's not just me.
Okay, now?
Can someone else confirm?
Yeah, I can hear him. I can hear him.
Yeah, I heard him talking too.
All right, cool. Yeah, so let me just repeat that last part. One thing that data frames that our dataset library is not is it is not meant to be a replacement for your existing data processing libraries. So we think that Spark and Dask do a great job at what they do. And what we want to make sure they do is we want to make sure that you can continue to use your favorite data processing library and have it integrate well into the Ray ecosystem. Okay, so this is sort of where we see Ray datasets fitting into the like general ML ecosystem. So if you have a lot of unstructured data, we still expect you to be using, doing ETL using your favorite pre-processing frameworks, whether that's Spark, Flink, you're pulling that from a data store like Snowflake or Delta Lake. We want you to use Ray datasets to load that data into your Ray cluster. And then we want you to be able to seamlessly use that data in any of your favorite training frameworks that are built on top of Ray, like RayTrain, Horvath, distributed TensorFlow, distributed PyTorch. All right, so let's take a look at the universal data loading aspect. So essentially here, Ray dataset's job is to essentially act as sort of the distributed version of Arrow. So we want you to be able to take your data, whether it's in a data frame already, like Modin, Dask, or Spark, or whether it's stored in storage, and move that data and store that data in a data set. Then now that we have it in a universal format, libraries like Horvath or TensorFlow or XGBoost only have to be able to work with a single distributed data format to be able to ingest data from any of these other sources. So it provides essentially a narrow waist. And the way that we're able to accomplish this is we really heavily rely on Arrow on the back end. So Arrow already solves this job on a single node. And so Dataset's job is to essentially distribute this. Cool. So this is just a quick slide showing some of the data formats that we support. You can go find a more up-to-date version of this table now in our docs. But as you can see, like we've really done a lot of work to try to support as many different input and output data types that we could. And again, like because we rely on Arrow, we were able to do a lot of this very quickly. Okay, so not only do we want to be able to read this data in, but we want it to be performant. I'm going to go over this section a little quickly because I think we're going to see later in Patrick's slides that a lot of this is not theory anymore. It's really practical. So we've tried to make it extremely easy to read and write from any type of storage. It should be one line to get your data into Ray. And again, we want it to be extremely efficient and extremely parallelized. And Patrick will probably talk in more depth about how he's able to use data sets with his library and get this performance in the real world and get it to scale up really, really well. Okay, so now let's take a look at last mile preprocessing. So with last mile preprocessing, we want to be able to support the types of operations that don't make sense to do while you're doing your typical data processing, right? There are things like random cropping or shuffling of your data that it doesn't make sense to redo that kind of work and like restore that kind of data in S3. And so we want you to be able to do that at the very last second in memory to be really, really efficient. And so for that reason, Dataset supports a lot of the like basic transformations and aggregations that you would typically expect out of a library like this, or out of like any data set or data loader. So you can do things like maps, batch maps, you can do filtering, you can do aggregations, and even a couple of global shuffle operations that if you come from a systems background, you may recognize as being really pretty challenging to implement efficiently and stably. And so just to illustrate what this might look like, if you have some kind of an input, you may start by taking that input, you may want to map it and like apply some transformation to each of your data points. And then you may want to do some kind of a shuffle or like group your data by some class, and then do some kind of reduction operation like like finding the averages or summing something, and then finally combine that back into an output. All right, cool. Yeah. So now another really important feature that Datasets has for efficiency is essentially pipelining. So for those of you who do not know what pipelining is, just a really brief introduction. Essentially, you can think of like a typical pre-processing pipeline like this. There are steps like loading, pre-processing, and doing inference on your data. And typically, if you try to do this naively, you may load your data first, then pre-process, and then start doing some inference. But the issue with this is that your GPU is sitting here idle, just wasting money while you're not using it. And so the idea with pipelining is that we should be able to use the GPU, we should begin to use the GPU as soon as possible and use it for as little time as possible. So in a pipeline version of this pipeline, essentially what we're going to do is you want to be able to immediately start doing your pre-processing once your first data points get loaded into memory. And then right when that pre-processing finishes, you want to already begin to do inference on that. And so if we do this, we can make a much more efficient use of our cluster and save a lot of money that way. And then finally, we also support windowing. So windowing is also really important because there are some operations like shuffling that you can't do over just a small portion of your data set. And so windowing can allow you to essentially execute a pipeline over just part of your data set. And of course, this works seamlessly with pipelining too. So just a little illustration of how this works. You may have a pipeline, you may have your data set workload do something like this without a pipeline, where you take a bunch of your data, and if it's too big to actually fit in your cluster, you may have to spill to disk, which is really, really inefficient. So instead, what you may want to do is, first of all, you can still do pipelining, but even with if your pipeline is too large, you can also split into windows and run your pipeline over a single window at a time. And sometimes there's a bit of a trade-off here in like model quality or something like that with performance. But in practice, we found that like this is something that people can do in practice, and the trade-off becomes well worth it. Okay, cool. So now I'm going to hand it off to Clark who is going to talk more about concrete use cases that people have been using datasets for in the real world.
Yes, thank you, Alex. Thank you for going through those slides, and also, yeah, apologies for thinking that your mic wasn't working when it was actually my headphones that weren't working. So hopefully we don't have any more technical difficulties on my end. Oh wait, that's not the right one. Let me.
I thought, Clark, you just wanted him to repeat what he said before.
Sorry?
No, I thought you just wanted him to repeat what he said before.
Oh, sure.
The datasets is not a replacement for Spark.
All right, this should, I feel like this keeps sharing the wrong screen. Hold on. I think I know what's going on. Yeah, let me try this again. Nope, that seems to be the wrong one. Yeah, let me try. Yeah, it's weird. This should be the correct window. I guess what window are you all seeing slides now?
Yeah.
Yep.
Okay. Okay, good. I'll just this isn't the window that I wanted, but I guess that's okay. Okay, yeah. So yeah, thanks again, Alex, for going through an intro to datasets and also a very great motivation. I'm super excited to talk about the two biggest use cases of datasets. Those two big use cases are super scalable shuffled ML ingest. This is loading data, shuffling data, and getting it to a distributed set of model trainers, such that you don't want the data loading or shuffling to be your training throughput bottleneck. And then the other big use case is doing batch inference very efficiently. And when I'm saying efficient, you really don't want to be wasting that GPU resource because those kind of cost money. So first, the scalable shuffled ML ingest use case, a little bit of background on this one. A quick overview of this use case. The core goal is to load data quickly into one or more model trainers. The primary functions here are loading the data from some external storage or maybe from another in-memory representation of your data set if you already have it in memory. You want to partition the data into a shard per trainer if you have multiple trainers. This will allow you to do data parallel training. And then you want to batch the data into GPU batches. This is going to allow you to saturate your GPU memory and increase your training throughput. It's good times. And then you want to shuffle the data before each epoch. And for those who think that are maybe saying, oh, why do I want to do that? I will fully motivate that in the next slide. For certain models, this can be very important. Right now, the current solution for per epoch shuffling is typically local shuffling. This is where you have an in-memory buffer on each trainer. And after that initial split of shards at the beginning of training, each trainer is only reshuffling their shard at the beginning of each epoch. And there can actually be issues with that if you're not shuffling across shards between epochs. And global shuffling, where you're actually doing essentially a full random sample from the full data set at the beginning of each epoch for each of those shards. This is better, as I'll show in a second, but it's also very hard, especially once your data set is too large to fit into the memory of a single machine. And or when doing distributed training. And so this is kind of just showing that data coming from a data source, your data loader creating those shards, and then feeding those shards into the trainers, the corresponding trainers. All right, so first, a quick aside. Why do we want to shuffle before each epoch? I thought I could just, shuffle my gigantic data set in Spark once before training, and then pretty much call it good, right? Well, the TLDR for this is that for certain models and data sets, per epoch shuffling actually gives you much better model accuracy for a given set number of epochs. And you can think of this as decorrelating samples within and across those GPU batches. And this is important even to do like on each epoch. And this per epoch shuffling reduces variance and improves the generalization of your model, and it prevents overfitting. You can think of this as batches being more representative of the entire data set, therefore improving the estimate of the true full data set gradient, which is certainly what you want. The gradient updates on individual samples are also made independent of sample ordering. You can think of certain data sets such as, let's say you were a certain transportation company and you had a lot of data samples that were temporally correlated, where you're finding that you would certainly not want, when training a model, if that temporal correlation is really, you're not wanting to represent that in the model, you might get some really bad overfitting on those temporal correlations if you're having your model just train on all of those samples in a row. So you definitely want to decorrelate there. And overall, per epoch shuffling results in improved statistical gain of each step in the training process. And we have some results later that show that that's the case for certain data sets and certain models. So first, why is this hard? You've probably, if you've only done single node training with smaller data sets, you're probably thinking this, I don't really want to think about this. This is just like, I just want to, load data into my trainer. Well, first, when your data set is large and you have a distributed set of trainers, you need to have some very scalable and parallelizable reading from your external storage. You don't want your data loading to become your training bottleneck, which it often becomes at a certain data scale. You also really want to avoid those pesky idle GPUs when you're reading and shuffling that data. If you look at this diagram here, if we are serially doing the shuffled data loading and then feeding that epoch's worth of data into the trainers, the GPU is sitting there idle during that shuffled data loading time. And those little red gaps, that's just completely burning money, which nobody wants to do. And a continuation of this, since there are many hard things at a certain data scale, the full pipeline might not fit into the memory of your number one of a single training node, and number two, it might not fit into your cluster as a whole. Even if you have a good many machines, if you're working on like many terabytes of training data, you're going to be encountering some issues unless you're creating a super massive cluster, which you might not want to do. That might be, that's a little bit like cost prohibitive. Local shuffles hurt your model accuracy. This is like the status quo solution is just to shuffle locally within a shard. It hurts your model accuracy, but the big issue is this global per epoch shuffling is very hard to do efficiently in a distributed setting. You are fundamentally doing like an all-to-all communication when between the maps and the reduces. And then not to mention that the chunks of data that you're creating in this distributed shuffle, you're creating n squared chunks, which can tend to be a big issue. But overall, with all of these difficulties of doing ML ingest at a large scale, we want to solve these problems, but we should really try to keep the API simple. Users didn't have to think about a lot of these problems when their data set was small and they were training on a single node. And ideally, they would still not really have to think about these problems. It should be all hidden underneath a simple, basically distribution agnostic API, if we can. So first, how does the datasets solution to the large-scale ML ingest problem address each of these issues? The first one is we need to have scalable I/O. And this is what Datasets has. We have super scalable parallel I/O, supporting all of your favorite storage backends and formats. If we don't support one that you really like, definitely let us know. And this is the API basically. As you can see, not much complexity here. You're just giving a storage URL, and then you're specifying some read time parallelism. And this basically roughly translates to how many parallel read tasks you want to launch. So for example, when reading from an S3 data set with like a parallelism equals 3, this would launch a three read tasks and then quickly load the data into your trainers. So hooray, scalable IO. And we actually do this by heavily leveraging Arrow's really great single-threaded IO, and then using Ray to parallelize that single-threaded IO functionality. And that gives you high performance within each of these parallel read tasks. And then Ray's distribution then results in really high performance, scalable distributed reads. The next bit of the dataset solution that helps us solve one of those problems is pipelining the stages in this ingest pipeline. So Alex mentioned this a little bit before. For this particular use case, we were wanting to pipeline pre-processing and shuffling with model training so we can keep that GPU saturated. If you remember before, this pesky GPU idleness costing us all this money, super, super annoying. With pipelining, by pipelining here, where if you see the green there, that's your shuffled data loading, and your purple is the training. By doing the shuffled data loading for the next epoch while training on the current epoch, you're able to fully saturate that GPU, and then also have some hot and ready GPU batches for your next epoch when it becomes time to train for the next epoch. And all that you really need to have here is you need to have that shuffled data loading throughput exceeds your like on GPU training throughput. As long as you have that, after the first epoch, you will always see like basically super hot GPU batches that are just being essentially read as a memory reference. Like in the most ideal case with prefetching, it should just be sitting there in the memory of the trainers, ready to go when you want to start training. So this ideally would eliminate the shuffled data loading bottleneck when looking at your overall training throughput. So for that per epoch shuffling, it sure would be great if we could do a super efficient distributed shuffle on Ray using datasets. Well, thankfully you can. As Alex mentioned before, a good bit of core Ray's data plane, in particular its distributed in-memory object store, is very amenable to efficient distributed shuffling. It's both a combination of zero copy references or zero copy deserialization due to some wonderful properties of Pickle 5 buffers. And then in addition to that, you also get zero copy shared memory reads if you have a chunk that's shared by multiple workers. And then object transfer is also very efficient with like some pretty smart back pressure while also providing parallel transfer by transferring over multiple threads. So we've been working very hard on this data plane. On the data plane of Ray, we actually also have a lot of work planned in Q1 that's very exciting. And so hopefully this will just continue to get better. Already it's pretty dang good. In addition to the efficient distributed in-memory shuffle, we also have locality-aware placement of these output shuffle shards onto the trainers. So if you look down here at this code, if you look at the split call, for the locality hints arg, we're passing in the model training actors. So these are basically, the actors here are like the training workers. With that locality hint, we do smart placement of the data shards onto the actors, such that when the training actors try and fetch the data should be already sitting there in the object store, and then it's a shared memory read, which should be super fast. So this is kind of showing that here where we're doing like on each epoch, we're doing a random shuffle, and then we are pushing that output to each of the trainers, pushing the corresponding shard. So we had that pesky issue, so many pesky issues at scale, but we had that pesky issue of how exactly are we going to deal with our data loading pipeline not totally fitting into the cluster's total memory. thankfully, we have the solution that we're calling windowing. This is where you're able to limit the size of the working set when doing the shuffle data loading. And this will limit the amount of data loading tasks, preprocessing tasks, and shuffling that's done at a time to just a small window of the data set, of the full data set. So you can kind of imagine it a little bit like this. For the first window, it's this little red rectangle. All that we're doing is we are loading, shuffling, and feeding that to the trainers, just that little partition of the input data. And then next, the second window, we fetch the orange one. And then for the third window, we fetch the yellow partition. And this way, instead of the total working set size being a factor of the red plus orange plus yellow, which if we have some cases of read amplification within Ray, or any other little intermediate copies hanging out, it can be quite large. It could be 4x, 5x of the total data set size. Instead, that multiplier of the working set size is only going to be for this red partition. So that keeps your total working set size down. And this is, by the way, going to still constitute a single epoch. We're still doing a full pass over the entire data set. But instead, we're just doing it within windows. And you may be thinking, oh, won't this degrade the shuffle a little bit? That's true. It's not degrading it to the point of a local shuffle buffer on a trainer. You would still be able to, your working set only has to fit into the cluster's total memory. It doesn't have to fit into your trainer's leftover RAM. So you're still getting better than a local shuffle buffer, but this does degrade the shuffle a little bit. Right now, this is a trade-off between how large you want your cluster to be and then the quality of the shuffle. In the future, there's actually no reason that we couldn't implement this windowing while still doing a completely random sample. It would just be a little bit more of a complex shuffling implementation, maybe a little bit more constrained in its use. So if that feature seems to be table stakes for you, definitely let us know, because we can tackle that. Yep, trading off shuffle quality with cluster size. And then finally, we wanted to address all of this with a simple API. Thankfully, I think we were able to hit that target. Here is just a little example of a trainer task, and this is just going to consume the shard of the dataset pipeline. Here you can kind of see the usage of that trainer plus datasets for data loading. So that trainer again is the consumer of the data, and here we show reading from some external storage, reading Parquet files. We repeat this read operation for the number of epochs that we want to train for, and then we shuffle each window, and then we feed the data set to the trainer. So this is the small data on a single node case. There's a single trainer here. We're not doing any windowing. This is the simpler case. To go to the more complex case of distributed trainers, a multi-node cluster, where we want to limit the working set size, all that we have to do is add this windowing directive, saying that we want no more than some number of blocks per window. Right now, this is expressed kind of with a little bit of our internal representation, where each partition of the data set we call a block. And this is saying no more, exactly 20 blocks per window, but we could actually eventually expose an API of actual bytes, saying no more than this many bytes in a single window. And then eventually, hopefully we'll be able to optimize this away where it doesn't even have to be specified, where you could just call .window, and then we would hopefully calculate the window size that can fit in your cluster for you. So you wouldn't even have to specify how exactly you want a window. And then the split there splits this dataset pipeline into a shard per trainer, and then we feed those shards into the trainers. And that equal argument, the equal equals true, that's just telling the dataset splitter, please give me equalized shards. So each shard will have an equal number of samples. Yeah, so some case studies for this use case. First, a little bit of background on a couple of these case studies. These are going to be some users that have had some success with using data sets for this use case. One common problem is the existing solution that they have for shuffled data loading is actually the primary bottleneck in their training pipeline. We actually encountered this more than we had expected. A lot of users that we had talked to, the actual training of their model was going perfectly fine, and their data loading solution, either due to pauses in their existing data loading solution where suddenly it would just hang for like tens of seconds, or even just like it was consistently like not good enough throughput in order to keep the GPU saturated. We saw both of those happen in the wild. The other common problem is that their models / datasets are shuffle sensitive. And this is where doing that local shuffle, where each trainer has a shuffle buffer, where that degradation in like the fully global random shuffle quality to this local shuffle actually affected their model accuracy, such that for like a fixed training window, for like a fixed number of epochs, they saw, comparing the local shuffle to the global shuffle, they saw worse model accuracy. At the end of those epochs. So the first case study here, it's a high-tech ML platform startup. This is anonymized because it hasn't quite been announced publicly yet. Their existing solution was Pandas to S3 to Petastorm to Horvath. So this is Pandas pre-processing here, persisted to S3, then loaded with Petastorm, and then fed into a distributed set of Horvath trainers. Petastorm, by the way, if you're not familiar, it's an ML ingest library from Uber. It's open source if you want to go check it out. So Ray's solution was to obviate the need for that intermediate persistence to S3, and instead move that pre-processing to Dask on Ray, and then have a very efficient exchange of that tabular data to datasets, all kept in memory, and then use datasets to feed the distributed trainers, the distributed Horvath trainers. The second case study, it's a large tech company in transport space. Can kind of let people guess about that, who that might be. And their existing solution was S3. Their S3 dataset was loaded with Petastorm into Horvath trainers, and Ray's solution wasn't to eliminate S3, it was just to use datasets to load the data into Horvath instead of Petastorm. And both of these case studies suffered from both of those common problems above. Both the existing solution is their chief bottleneck, and their models are shuffle sensitive. So benchmark results. I'll go a little bit quicker because I feel like I'm a little bit running short on time. Dask on Ray and datasets for the high-tech ML platform startup. This is where we obviated the need for S3. The Dask on Ray and dataset solution was 8 times faster than their old solution, even on small data and cluster scales, which was actually somewhat surprising. So their benchmark, which was using the New York City taxi dataset, and then a single large GPU instance, they saw that Ray, by the way, here, lower is better because this is runtime. They saw huge improvements using Ray compared to Petastorm, compared to just all in-memory pandas. And even when adding custom optimizations to Petastorm to do some like async prefetching, Ray was still doing far better. And for that large transport tech company where we were only replacing Petastorm as the data loader, still loading from S3, datasets was 4 times faster than Petastorm when loading from S3. And this benchmark was on a pretty large data set. It was 1.5 terabytes of synthetic data, all tabular data. And then they were using 16 nodes, 2 shuffle windows. And here is showing like the difference in aggregate throughput. So this is the throughput of all combined 16 nodes. So as you can see, we got like around 4x higher throughput. So Ray datasets is giving both higher quality shuffle and better performance, even at small data scales, at small data and cluster scales. So that last little qualifier is actually surprising. At larger scales, datasets really shines. We're also actively working on some comprehensive open benchmarking, so stay tuned for that. Yeah, I'm wondering, hey, hey, Jules, do you think I got time to quickly go through the batch inference use case? I'm not so sure.
2 minutes. 2
2
minutes.
minutes. All right,
Yeah.
lightning round. Okay. What exactly is batch inference? This is where you want to run model inference over a large number of images. So obviously you batch. The functions of this use case is you load data from storage, you do some minor pre-processing before the inference, and then you perform model inference on the batches of data, possibly on the GPU, often on the GPU, and then you save the result back to storage. And we want to do it all efficiently. So what are the big challenges with distributed batch inference? Scheduling, number one, you don't want to have to transfer data around the cluster as you're going from pre-processing to doing the batch inference on the GPU. You only want to reserve GPUs for a fraction of the time. You want to be able to use GPUs as a fractional resource. And you need to keep the GPU saturated to keep costs down. Like, again, pesky GPU idleness. Look at all of that time the GPU is staying idle while we're loading and pre-processing. So the dataset solution solves this with automatic data locality, number one, less object transfer when going between pre-processing and inference. We utilize Ray's resource scheduling. So you look at how simple that API is. We're using the map batches, which maps an arbitrary UDF across batches of the dataset. And the num GPUs equals 0.25. There you go, you got your fractional GPU. And that's the really nice bits about Ray's resource model. It's that simple, you know, to request a resource. So first of all, the dataset solution, how do we get really good GPU utilization? That's by doing the pipelining, which Alex mentioned before, of the data loading, pre-processing, and inference stages. And look at that, the GPU idleness shrunk all the way down with this wonderful pipelining. So this is just by overlapping data loading, pre-processing, and inference. And you're still able to get pretty good parallelism. It's basically just a trade-off with you know, latency for the final stage and parallelism, basically. And again, very simple API, wonderful. So quick case study. We have a startup that's processing aerial imagery, and they're looking for a scalable and resource-efficient batch inference, wonderful. And then the same high-tech ML platform startup, their existing Pandas Torch solution was not scalable, made very inefficient use of resources, a lot of idle GPUs hanging around. And so this integration was a Dask on Ray to Ray Datasets to Torch pipeline. Benchmark results, Dask on Ray plus Datasets plus Torch was 5 times faster than Pandas and Torch. Again, even at small scales, which we were thrilled about. New York Taxi dataset, once again, single large GPU instance. And here we're seeing higher is better because we're looking at throughput, comparing Dask on Ray and Datasets and Pandas. And as you can see for these two different throughput on the left, runtime on the right, Datasets was doing super well. For the larger size, Pandas couldn't even complete. That's why there's like Pandas, I believe the Pandas workload crashed. And that's why it's no longer, that's why it's not there for the right data points, the data points to the right, larger data sizes. So again, Datasets provides better resource efficiency and better performance, even at small scales. So finally, a summary. There's lots of room for improvement in the status quo of ML pipelines. We want to reduce cost and performance overheads. We want to support ML operations like shuffling at scale. And we still want ease of use. We want the APIs to be simple. Ray Datasets hits these marks wonderfully, I think, with efficient data movement between steps in a pipeline using like locality-aware scheduling and locality-aware placement of data onto trainers, hyperscalable implementations of common ML operations. We've got a simple expression of these complex ML pipelines. It was just basically 5 to 10 lines of code for these two different use cases, which could normally be hundreds of lines of code. And then for ML ingest, you get much better shuffled data and better performance in the status quo. It's not even a trade-off. You know, you get best of both worlds. And then finally for batch inference, better efficiency, better resource efficiency, and performance in the status quo. All right, thank you. Here are some resources. 3 minutes over, well, without much time for Q&A.
Well, thank you. Thank you very much, Alex and Clark, for this brilliant, in-depth technical discussions about Ray sets. all its efficiency, all it can actually do for you. We do encourage you to try it and give us a particular feedback. I think we have time for maybe 2 questions at most. And I think these answers to the question, we can actually post it on a separate document. But here's a question for you, Alex or Clark. When would Ray datasets be appropriate in contrast to modern? I think Clark, do you want to take that because you were about to type that in?
Sure, yeah. Oh, you saw me?
Yes.
Yeah.
I can.
We're primarily considering it appropriate for simple data processing. Basically things that you can express with like a map or a batch map or a filter. So very, very simple. In terms of like the use case, we're really focusing on pre-processing for training and pre-processing for batch inference. So this is kind of like the last mile stuff, stuff that doesn't require a huge distributed join or a very complex like data frame munging and operation. This would be for like some very basic last mile stuff. And we're going to have some better support for common pre-processing operations like, like standard scaling, one-hot encoding. We're looking at adding some nice helpers for those to make it very simple.
I think, yeah, go ahead.
Oh, I was just gonna say, but really with map and filter, you can do most things. You can do a lot of things. All that we're missing really is reduce, and then you can do pretty much everything, but then it'll be a question of UX. Yeah.
I think one thing both of you might have touched on the per epoch shuffle, but I think there's a related question to that. How does Ray Dataset support the shuffle operation? Do we actually have a dedicated shuffle service, or is it something that's actually done by the actor, or how do we actually have a notion of shuffle service like Spark has a notion of shuffle service?
This is currently right now, it's hard, it's like a hard-coded implementation by us. So this is just basically doing like a map reduce shuffle. So using map tasks to chunk out the data, to chunk out the existing data set, and then like each reduce task then gets a mapper chunk from each of the mappers, and then the reducer then shuffles all of those mapper tasks and outputs some shuffle data, and then that data at the end is essentially concatenated. So it's a datasets native shuffle. It's a Ray native shuffle, but we could certainly look at instead like making that more pluggable. Like maybe it is like an external shuffle service, but we would like to do it, I think, in-house efficiently if we can.
Yeah,
Go ahead, Alex.
Just to add to that, I think maybe when you're thinking of a shuffle service in Spark or something, you're thinking of like some central coordinator or like scheduler that's responsible for scheduling where these like shuffle tasks are going to occur and scheduling the like network requests across the network. Whereas in Ray, we rely heavily on the object store for this, and so we could go on a whole another hour-long talk about how the Ray object store works. But the short answer here is that we allow the object store to handle the shuffle for us. And the object store handles this in a more of a peer-to-peer fashion. So if you take a look at some of the talks and papers published on how Ray's ownership model works, you'll see a lot of there's a lot of details there on exactly how worker nodes communicate with each other in order to like do a stable shuffle.
Yeah, there's a great blog post by Stephanie Wang, who's an engineer at Anyscale, on how Ray does an efficient distributed shuffle.
Yes, I'll go ahead and post those links, both the ownership model as well as the blog post you're talking about.
Yeah.
I think we're out of time. I want to give enough time to Patrick. We're going to shift a little bit now, hear from the community how the Ray datasets is actually being used at a massive scale to build a data catalog at Amazon. And when you think about data, you think about scale at Amazon. So joining us is Patrick Ems. He's the senior software engineer in their big data group, and he's going to talk about how they actually use Ray and Ray dataset to build a Delta catalog. Yeah.
Thanks,
so there you go. Take it over, mate.
All right, appreciate it. So first things first, can everybody see my screen? Going to enlarge the slides here if you can all see it.
Yes, we can see the beautiful cat.
Okay, perfect. Yeah, thanks for the sound effect there. It matches the intro slide here perfectly. So yeah, we're going to be talking here today about the DeltaCat project. So a little bit of background before we get into it. So I'm Patrick.
I'm a senior software engineer at Amazon, and I've been spending about the last 6 years of my life primarily working on business intelligence problems at Amazon, especially data management and optimization problems for our data catalog at Amazon. And so one of these problems that actually led to this project is trying to make our data catalog more usable for Amazon's data scientists and machine learning engineers who prefer to interact with the catalog in Python, but also don't really want to be constrained by the single process constraints of historic Python. So that kind of led us to Ray, and we spent about 2 years actually leading up to the contribution of this project in trying to integrate our data catalog with Ray and create more Pythonic APIs for data scientists and machine learning engineers to interact with data catalogs. And we found a lot of these things we did along the way are generalizable to a lot of data catalogs that exist in open source today. And so thus the DeltaCat project was born, and we contributed it to open source as part of the Ray project. It's still in a pretty early phase of development. We'll go through what we do with it today at Amazon and what we're going to do with it in open source in the future to make it more generally useful for all of you. It's a quick intro here. So what does DeltaCat mean? DeltaCat there stands for Delta Catalog of ACID Transactions. So sorry, it has an embedded acronym, ACID being atomic, consistent, isolated, and durable. You see that terminology a lot in the database world in particular. And today we're going to be looking at it, especially from the perspective of how it kind of extends Ray datasets and enhances the Ray dataset ecosystem and uses Ray datasets to bring you a better experience with your data catalogs. So before we get too deep into technical details, let's start out with an introduction to what data catalogs and data lakes are. So this is sometimes a hotly debated topic, the exact definition of a data lake or a data catalog. But for the purposes of this presentation, I'm going to say a data lake is effectively a centralized repository for structured and unstructured data. And importantly, it allows you to durably store and retrieve raw data. So it's basically plain old bytes in, plain old bytes out. Examples of this are HDFS, S3, Azure Data Lake Storage, Google Cloud Storage. You'll often use these as a data lake just to put your stuff there, durably store it, and then retrieve it and trust that it didn't munge any bytes or do any post-processing on your data. And then getting into data catalogs for the purposes of our presentation and for how DeltaCat thinks about them is something that enriches a data lake with additional metadata. And so often that additional metadata will include things like discovery mechanisms. So you'll introduce namespaces that tables exist within. Tables will be divided into partitions. Maybe you'll have revisions of a table, things like that. Interpretation instructions, schemas are introduced, constraints are introduced. Content types and encodings are stored. And you'll get key insights. Maybe you'll just have human readable descriptions of your table, audit logs about what people did, pre-computed aggregates. And I've listed a few things that include data catalogs as part of their open source project, like Hive and AWS Glue, Apache Iceberg, Nessie, Apache Hoodie, and Databricks Delta Lake. Now, these are not just data catalogs. They are all kind of ecosystems unto themselves, but I would argue that all of them include a data catalog at some level of their infrastructure. And the current state of these data catalogs and Python integration is something that we were having trouble with at Amazon. So usually when you're dealing with data catalog data, you want to read data from a data catalog, you want to write data back to a data catalog. You'll use an integrated compute engine with that data catalog. 3 of the most popular ones might be Hive, which will provide you PyHive and HiveQL, and PySpark in the Python world, which is a little better, gives you Spark SQL, data frame streaming, and a little bit more Pythonic offering of pandas on Spark there. And then PyFlink, which gives you Pythonic versions of data streams and tables. However, our data scientists and machine learning engineers were entirely happy with the experience of using these things, notably because they were based on the preceding Java and SQL APIs and architectures. So they weren't really made for a Python native experience. They weren't really made with delivering Pythonic APIs first and foremost. And thus they tended to have limited feature support versus their Java counterparts and their SQL counterparts. The APIs weren't always terribly Pythonic, and this would sometimes make things inefficient. The Python world would have to maybe call into the Java world and do cross-language integration overhead there for like Serde work. It's not always a pretty picture for those of you that have tried to integrate Python applications with Java backends and stuff like that. It's complex, you have efficiency problems, and sometimes you have to create a new Python native layer to resolve those efficiency problems. So kind of being a little unhappy with the state of data catalogs and their integration with Python, we decided that we would start looking into the demand for a more Pythonic data catalog. And so here's a quick diagram from /data here from a survey that they ran in Q3 of 2021, the relative size of Python communities. And you can see they categorize Python as the second largest programming language community there. And it's interesting to note that they noted it's most popular in data science and machine learning. The actual report noted further that nearly 70% of ML and data scientists are using Python. And the runner-up is R with 17%, so they're far and away the leader there. And interestingly, least popular in data science and ML is Java, the thing that's the chief supporter of your data catalog integrations in open source right now. So we kind of saw this as good motivation for pursuing this project, not just for ourselves, but for the benefit of the general community of data scientists and machine learning engineers. And also as additional motivation, they also did this interesting report. The number of machine learning developers and data scientists involved in each stage of the data science and ML workflow end to end. So you see, not very many people are involved in all stages of the workflow end to end, around 10%, but the highest percentage of people working in one stage of the ML workflow would be the data exploration and analysis stage, which is really the stage that we're looking at here. And we want to meet these developers where they are and provide them, if they prefer to work in Python, as the stats seem to clearly show, then we want to give them Pythonic APIs and a Python native experience for working with their data catalogs and doing better data exploration and analysis there. Okay, so we set a few goals for the project here. We want to first provide intuitive Pythonic data catalog APIs. And two, we want to bring fast, scalable ACID transactions to Ray. And third, we'd like to give Ray users a consistent, portable interface for interacting with data catalogs. So that means, you should be able to use the same interface either through Ray Datasets or DeltaCat interfaces in order to interact with multiple open data catalogs or cloud data catalogs. You shouldn't have to rewrite your code. And we also want to provide scalable, efficient, and reliable implementations of common data catalog table management jobs. So there's a lot of things that go on in terms of schema evolution, compaction jobs to create read-optimized views of tables, which we'll talk about a little bit later, that require some heavy lifting from distributed compute technologies. And we want to build those in and create as optimal implementations of those as we can to support your workloads. And so if we take a look at the ecosystem here, this is kind of inspired by the Ray Datasets ecosystem diagram. That shows where Ray Datasets leaves off and where DeltaCat picks up. So we want it to basically be an extension to Ray Datasets. So we want to support all the same data types as input and output on our Ray cluster. But when you add DeltaCat to the picture, we want you to not only be able to read and write from just raw data storage and data lakey solutions, but we want you to be able to manage tables effectively inside of these other open source products that include data catalogs as well. And then, these often have good integrations with your data warehousing solution and kind of closes the gap from your data warehouse to your data catalog to any machine learning that you may be running. So it gets you a more kind of orderly picture for managing your data and integrating it with your machine learning workflows than you get from just a pure data lake. Okay, and so we introduce a few core interfaces here to try to solve this problem on a technical level. We introduced the storage interface, which is a low-level interface with a target audience of data catalog developers looking to integrate their catalog with Ray. So if you're a developer of Apache Hudi, of Iceberg, of Delta Lake, we'd like to talk to you, and we'd like to make sure that the storage interface is suitable to represent your data catalog and data storage layer, and that it could be implemented so that Ray could easily interact with it. And this exposes basically lower level catalog metadata models and their structural details, table partition details, table revision and CDC, that's change data capture, delta log details. And you can find a link to that interface on GitHub, as it exists right now there. Then we have a higher level interface, the catalog interface. We expect that this is what the majority of data catalog users will use to integrate their data with Ray. And the default implementation of that should use the storage interface. So basically all the code is written against the storage interface to make these higher level operations exposed by the catalog happen in the storage implementer of choice. So if somebody uses a catalog method to write to a table and they're using a storage interface based on Iceberg, the storage interface should commit the results of that write to the table using the Iceberg table format, for example. And so again, we're exposing table level writes of Ray datasets and table partition and incremental or time-bound, or you might say windowed reads into Ray datasets. And you can see, again, the interface for that there at that link in GitHub. And again, to dig into the target audience a bit more, we're targeting two main groups of users here. One is data catalog developers, who we expect usually want to implement the storage interface, the lower level interface. And by so doing, they can reuse existing Ray catalog management job implementations. So anything that we've already written to compact your table, provide read optimized views, stuff like that, it just works out of the box. And they can also reuse existing catalog implementation based on the storage. But maybe they sometimes find that they don't fit perfectly into the storage interface and they want to implement the catalog interface. And now this means they wouldn't reuse those managed jobs already, but they could support more flexible storage models. And apparently I didn't finish the sentence there, but support more flexible compute models. That's what I was going to say there. And data catalog users will usually use the catalog interface because it provides a simpler, safer standard API, and sometimes use storage interface, which is complex. It has less guardrails, but it's a more powerful API. And Delta Cat Compute, these managed compute implementations that we're talking about that are implemented using the storage interface, are powered by Ray. They're intended to be invoked transparently by the Delta Cat catalog API. You shouldn't generally have to invoke them explicitly as a catalog user. They will manage and curate your catalog for you quietly behind the scenes. And current implementations we have are compaction, as we talked about, which merges table partition, change data capture, or delta logs into a single unified view of the table. And statistics, we also have some basic statistics calculations for table management, which calculate column delta partition and table level statistics for everything in your data catalog. And we have upcoming implementations we're working on for schema evolution, table repair, and ML-driven anomaly detection. Okay, and so with that kind of context out of the way, let's get into some code. If you were to use Delta Cat, how would you use it? Well, you start by initializing it and registering available catalogs. In this case, we're registering just one catalog. We're going to call it the prod catalog. You have to provide it an implementation. So I'm saying, okay, this is the guy that implements my interface. And then everything else is just keyword arguments that this catalog implementation takes. So in this case, we're saying we had an S3 catalog, perhaps minimally we'd need to provide it the base URI of this S3 based catalog to find all of the files and all of the metadata that create our catalog. When we call this, Ray will be initialized automatically via ray.init with address equals auto. And if you only provide one catalog like we do here, it will become the default. So you don't have to provide the name of the catalog in future operations when you're writing tables or reading tables or altering tables or whatever you're doing with your catalog. But you could also give a default catalog name if you're providing multiple catalogs. Maybe you have a prod, beta, alpha catalog. Maybe you have an Iceberg catalog and a Delta Lake catalog that are both production, things like that. In that case, you could specify a default catalog yourself and say, well, if I don't specify a catalog name, assume that this catalog is the default. You can also give custom ray.init args. Okay, and so once we've initialized the catalog, how do we go about actually creating and writing data to a table? Maybe one of the first things you'd want to do. So in this case, we're just going to create a simple ray distributed data set from a tiny 3-row, 2-column pandas data frame. Okay, and there's first 2 lines right up there, and then we're going to write this data set to a new Parquet table named sample table in the example namespace of the prod catalog. We're going to say, hey, I expect the table write mode to be create. So if the table already exists, you're going to get an error, and please write the content type out as Parquet right there. Now, actually, it's equivalent to this command below, which is much simpler. So the top command is a very explicit way of creating this table and writing data to it. But actually, all of those arguments would have been inferred if we just gave it a data set and a table name, because we would have known the default catalog is prod. We only have one after all. It would have resolved to a default namespace that catalog provides. And we would have seen that the table exists and assumed that you wanted to create it. And the default content type would also be Parquet. And so now let's take a look behind the scenes about what actually happens here. So you start with the data set that we created, loaded onto your Ray cluster. And the first thing that will happen is we will stage the table inside the catalog. So it should not be visible to other users of the catalog yet. Since it's not committed, just staged, we created a metadata container for it that's not queryable. And then we will create, or stage again rather, delta metadata that's not discoverable by other users. We've staged an append delta that we're going to put inside of that table. And for our implementation at Amazon, we are going to then load this data set into a Parquet file in S3. This doesn't have to be S3. It could be any viable storage plane. And some of the minutiae of the details here could vary a little bit from one catalog implementation to another, but they'll generally look about like this. And then since a delta, fundamentally at core, the model of a delta is basically to store one or more files together with metadata about those files, we're going to store a reference to the URI of this Parquet file that represents what we'd like to append to the table. And then we're going to commit the delta to the table, which is staged right now, again, not visible. So people still can't query it. And once we verified that it's been committed successfully, we will commit the table, which makes it discoverable, queryable by other users. So if you are another user, maybe what you want to do now is read that table back into a Ray distributed data set. And maybe just for fun, we'll convert that to a distributed pandas data frame using Modin after we read it back out. We'd expect to read this table that we put on the bottom once we complete this read. And again, just to make it clear what we're talking about, going back to the same diagram, the read of the table will be served directly against DeltaCat table metadata and be loaded into a distributed data set on your Ray cluster. That data set will be copied into a distributed data frame. These will both be subject to normal Ray garbage collection policies. And that is the end of that operation. It would have still had to read all that data from S3, but it figured out where it was in S3 by asking the DeltaCat catalog to describe the table, its metadata, figured out there was one delta in it, and that one delta had just one file in it, and read that into a data set. So pretty simple. And now we can also append another delta to this table. So we can just create another pandas data frame to append. Notice we're not even making a data set this time. We can kind of transparently accept either local tables. So this would be things like pandas data frames or arrow tables or NumPy arrays, and data sets as well for the data argument of write to table. So in this case, we're just making a local pandas data frame. We're saying, let's append this to the same table. If we append it to the same table, our data in column 1 is 1, 2, 4. So we see 1, 2, 3, then 1, 2, 4. In column 2 is DEF. So we see A, B, C, D, E, F. So we just concatenated those two tables together. That's what we expect to be the end result. Now it's a little more interesting to see what happens behind the scenes here. We start with an already committed table to the catalog. We create the delta, or stage rather, the delta again, that will be put in that table. Nobody can see it yet but us. And after validating that the data is consistent with the constraints of the table, like the schema and so forth, we will write its data to S3 or whatever file system you're using, reference that file just like we did before inside of the delta, and then we will commit it to the table. And now your write operation is actually done. It can synchronously return successfully. But if you keep on doing this over and over again, you inevitably face a problem where if somebody has tiny data sets like this that they keep on writing to the table with great frequency, you end up with a table that's very inefficient to consume because it had too many tiny updates. Now we can take care of two large updates at load time. We can split those in to read optimized file sizes, but there's not much we can do about you only had 3 rows to load. Okay, I guess we got to put it in new delta, except we can create either synchronously or asynchronously, your choice, a read optimized view of the table. And that's what our compactor does. So either synchronously or asynchronously, we trigger a compaction job against this table. It says, I want you to take that and I want you to create a read optimized view of it. And what happens there is the compactor will launch, typically on a separate dedicated array cluster. And it will read the deltas from this table. So it read both of those deltas that we just put in there. You could also, by the way, read those deltas yourself. So you can get incremental views of the table. You can limit it to just the deltas you want to read. You don't always have to read all of the deltas from a delta stream of a table. In practice, you would do that by providing like epoch timestamp or date ranges of updates that you would like to read. And so after we read those deltas, we're going to create or stage a revision of this table that people can't see yet because it's not yet completed. And then we're going to do a simple merge of those two deltas. Since we're using PyArrow here, this tends to be very efficient. It's a 0 copy merge. We're just taking pointers basically to the arrow buffers for those tables and stitching them together to create the merge table there. So very efficient when it happens on our Ray cluster. And then we are creating the compacted delta or the read optimized delta. This will be very useful if you're doing data analytics tasks over this table. And we're going to again write that merge table to S3. It's a new Parquet file. We're going to reference it inside of that delta, and we're going to commit the delta to our stage table, and finally commit the read optimized revision. And so from now on, when you read the table, you can make an explicit choice if you'd like about, I'd like to read the read optimized version of it, or I would like to read the incremental change log bound by this window of time. So by default, they'll both be there. There's kind of more advanced topics that we'd save for a later discussion about garbage collection policies, and maybe you want to get rid of the delta change log after you're done with this operation. That's a possibility, but by default, we will keep them both around. We won't replace or overwrite the delta change log. Okay, so we've talked about how an append works and how you can create a read optimized view to resolve problems that you would get from appending lots of tiny deltas. And now let's talk about a different mode of writing to a table. Maybe we create that same pandas data frame that we appended as the second delta before, but we instead say we would like to do the replace mode. So table write mode dot replace. So what's going to happen when we do that? What's going to happen here is we are going to create a new delta just like we did before, going to commit the Parquet file to S3. And again, you don't use replace to change the schema of your table. You don't use it to change its constraints. It still has to, be consistent with all of your existing tables constraints, but you can replace all of the data in your table with a replace type write mode. So we create that new data, and then we simply create a new revision of your table again. And we put that new delta into this revision of your table to basically replace all of its old contents. So again, it's kind of an explicit mode of saying, get rid of that old delta change stream, or keep it to the side, perhaps for historic reasons, but also make this purely replaced revision available and make it the latest revision, which will be queried by default if somebody doesn't have a preference to look back at the old delta change streams for the table. So that's the replace type write mode. And now another thing that we can do with these tables is we can create a table with primary keys. And this is something we focused on optimizing a lot. And we think it's kind of a unique feature of our catalog is primary key enforcement, or near real-time primary key enforcement, when you're creating tables with primary keys and appending to them. So in this case, we've specified one additional argument. We've said we want column 1 to be a primary key this time. Now, a primary key means it needs to be, every value in it needs to be unique and non-null. And so when we want to append another delta to it, we'll specify the merge write mode. By default, this will be an upsert merge. And we want to merge the same table that we did before into it, this pandas data frame of 1, 2, 4, DEF. And we expect the end result to be a bit different though than when we just did an append. It shouldn't be just a straight concatenation of the two values, but rather we should do an upsert merge, and this should be our end result. And the actual process to rectify this looks a lot like the whole process we went through for the append process before. You'll initially just create the delta, you'll commit it to the delta as an upsert delta, but then you'll trigger a synchronous or asynchronous compaction job to create the merged table. And here we've identified the updated rows in orange, the inserted row in red, the unchanged row in white. 1 and 2 both conflict on the primary key, and so we are getting the later values, D and E replaced over A and B, and we're getting 4, a new value, 4 and F inserted right here. Okay, so that's what we do with primary key tables. And we can quickly enumerate our current supported write modes by table type. Currently, as we're using this internally, we support for standard tables that primary keys, appending deltas, or replacing the whole table with a new delta, but we don't support merge upserts and merge deletes because we don't support merges against arbitrary keys yet. And for primary key tables, we don't support pure appends yet, but we do support replaces, we do support merge upserts and merge deletes. We're looking at closing these gaps and supporting all types of these going forward. It'll probably take some time. And finally, let's get into some benchmarks. How does this all work for us in terms of real world performance, integrating with Ray datasets and integrating with our data catalog at Amazon? Well, first off, we did 100 samples of DeltaCat read table from our production catalogs that were less than or equal to 1 tebibyte in size. Again, they were all stored in S3. We separated the results here based on whether they were Parquet or CSV. Technically, any delimited text, it's not necessarily CSV files, maybe it's TSV tab separated, but same relative performance. We ran these both on equivalently sized 8 R5N 8X large clusters, 256 vCPUs per cluster, providing a maximum network bandwidth of 200 gigabits per second. We ran an average of 304 dataset files per table. Average dataset size was 161 gigabytes, or about 67 million rows. 143 gigabytes, or about nearly 90 million rows for CSV. And our performance figures, we thought were pretty good. You know, we're looking at 7.84 gigabytes a second, or 63 gigabits per second, 28 terabytes an hour for Parquet. A little bit lower performance for CSV, 41 gigabits per second. About 2/3 of the performance here in terms of byte throughput, 5.13 gigabytes per second. It is interesting to note, however, that the rows per second per core is about equivalent, which points to a pattern of our production users usually storing tables with smaller row sizes in CSV and larger row sizes in Parquet, because then they can just select individual columns to read out. Because, well, I guess as they get larger, the rows per second is probably getting unacceptably slow for them in the CSV format. And the price is pretty good, basically saying costs you about 76 cents to read a terabyte of Parquet data, or a little over $1 to read a terabyte of CSV data. Okay, and now something we're a little more excited about and that we've worked very hard on. This is one of the things that we were looking to improve with our integration with Ray, is the speed at which we can do primary key merges. And so we did 432 merge upsert samples with prod datasets greater than or equal to 10 tebibytes. And now these figures here are measuring the performance of just the compaction merge stage. So we're not measuring the end-to-end performance of writing every piece of data, but like if you're running an asynchronous compaction job that comes back to it and compacts it later, how long will it take? That's the performance we're measuring here. So again, all the data is stored in S3. This time the content type is purely Parquet, which is fairly consistent for very large tables in our catalog. We generally want to represent those in Parquet. And so we've highlighted our best performing test case here, which was blazing 3176 gigabits per second. So that's over 1,400 terabytes per hour. And the largest input size that we were able to compact on a 110 node cluster, notice it's actually smaller than the cluster above, was 1.2 pebibytes. So much larger than actually the memory that this cluster has available on it. So we can limit the amount that we intake and we can churn through it at a pretty good pace still. So obviously our performance takes a hit since we have to pull it into the Ray cluster in rounds and merge things in rounds and then come out with a final result. So it's not quite as fast as the above performance figure, but still pretty fast, still 388 terabytes per hour. And our most efficient use case here is on an 11 node R5N8X large cluster. We dealt with a 22 terabyte input file, and we were able to process it for 22 cents a terabyte, or 61,477 rows per second per core on that table. And here are your averages below. The average efficiency, I think, stood out to me as very, very good, in particular, 33 cents per terabyte to merge primary keys. And the performance is quite fast too, churning through 749 terabytes on an hour on an average 130 node R5N8X large cluster with about, a little over 4,000 vCPUs. Okay, so what's the current state of this at Amazon? What are we doing with it? How are we using it? So we have a DeltaCat storage, that interface we were talking about earlier, the low-level interface, implemented for our production S3-based catalog. And we're incorporating it into the following novel use cases first. So it's unlocked some new realms for us here in terms of new projects and initiatives we're able to do. And one of those is near real-time table statistics and data quality analysis. And another is interactive data exploration and analysis for ML workflows. Two new initiatives we're using it for and spinning up projects for. And then another one is actually the compaction figures were so good that we are looking to migrate our legacy compactor on Spark EMR over to the DeltaCat and Ray compactor because we're looking at a reduced cost of about 91% in terms of dollars per byte processed, improved scalability, about 12 times larger input data sets, improved throughput, about 13 times larger in terms of bytes per second. And we can actually offer, we have very consistent job completion times. We can estimate based on the stats we've collected a very accurate completion time for the job. And we find that I think it's about 99.6% adherence rate to the SLA or the time we calculated the job being done by. So we can start to promise people, yeah, your data is going to be ready by this point in time. And we are over 99% sure that it will arrive at that point in time. Okay, and so what are next steps with this whole project? So, well, if you visit the GitHub repo right now, you'll notice it's very sparse on documentation. We have a few sentences written about what it is and what it aims to be, but we need to add a lot of diagrams like we went over here, a lot of specs and documentation to the interfaces and APIs, what they are and how to implement them and what the expected results are. And something that'll really help with that and help you all actually get your hands-on experience with it is contributing a reference DeltaCat storage implementation back to open source. So we have one for our prod catalog. We don't have one in open source yet. So you can kind of peruse the interfaces, peruse the models, peruse the compute implementations that we use, but we need to actually provide a real storage implementation for you to interoperate with your data catalog, and then use that to provide a reference data catalog, DeltaCat catalog interface implementation. So it's just so much easier for you to use and interact with. We're also looking at more native Ray dataset API integration. You shouldn't really have to go to these DeltaCat catalog APIs, in our opinion. You should just be able, if you have something in a Ray dataset, you should be able to use Ray's existing data IO APIs to read or write datasets directly from data catalogs that DeltaCat supports. And we're also going to write some more introductory and technical how-to blog posts that kind of teach how to use this and different patterns and anti-patterns for using it and how it fits within your workflows and examples, cool stuff like that. We're also working with Apache Iceberg right now on Apache Iceberg integration and the accompanying PyIceberg project. So hoping to have an Apache Iceberg implementation of the DeltaCat storage interface, ideally by the end of this year. So stay tuned there. And then also we're looking to transition core Amazon table management jobs to DeltaCat. So again, we're talking about managing an exabyte scale catalog, taking on over 70,000 jobs a day on average, and handling over 1 petabyte of new deltas a day. That's over 5.5 trillion records a day on average, and over 17 petabytes of deltas a day, or over 80 trillion records a day on peak. So, and this is just the fraction of the data catalog jobs that we're looking to take care of. Both this year and probably next year is where we're really targeting more production integration and migrations over to Ray and DeltaCat here for these data catalog management jobs. So massive scale, doing a lot of shadow testing right now to validate that we're ready and that it won't be operationally painful. Once we put it up there, we'll all be very smooth and successful at this scale. So those are our next steps. And yeah, thanks everybody for viewing. So yeah, any questions or comments, or if you want to get involved, please reach out to me, visit us on GitHub, give us a star, fork, whatever, and we can work together. And feel free to reach out to me on the Ray community Slack. All right, so thanks everybody.
Well, thank you, Patrick.
Happy to take your questions.
Thank you, Patrick, for the wonderful validation of scale. When you're talking about scale, this is what you're actually showing. There was a question that somebody asked, was going to ask or did ask, what were the largest data sets that Amazon worked with respect to data sets, and how big was the compaction file? And you pretty much answered on that colorful, colorful slide of yours about benchmarks. My question was, when you were talking about the compaction, you say you actually have a job that actually runs on each and every node to do the compaction. So are you taking the change catalog for the Delta and distributing it across all the nodes to do the compaction, and then you're doing a reduce? How is the final compaction is done? Could you elaborate that on a little bit?
Yeah, sure. So the first thing I'll say is I gave a talk that goes over kind of the design of that and how it works in depth end to end at the 2021 Ray Summit last year. And that's still accurate. That hasn't really changed at all. I think it's called Petabyte Scale Data Lake Table Management with Ray, Arrow, and Parquet. And so that will give you an in-depth view of it. But the quick view is, yeah, we do take all the deltas from the table. We basically keep a high watermark of what have we not compacted, right? So you have this high watermark of, okay, these are the deltas that are new, that have arrived, that I need to merge and create this new read optimized view of the table via compaction. And amongst those deltas, we actually go through a distributed hashing process first. So it's a multi-step kind of map and reduce-y sort of process that's been optimized for data catalogs with this delta changelog structure. And yeah, we start basically by hashing all these deltas across the Ray cluster into different hash buckets. And each hash bucket then is allocated by primary key value. So you would find all duplicates within the same hash bucket. We try to keep then carefully sized so that a hash bucket fits on a single node in your cluster too, which is another bit of a trick there. And actually, it's interesting that this process, we only read the primary key columns and like sort key columns. So we read drastically less data than, like, if you look at the read dataset benchmarks, they're lower than our merge benchmarks, because read dataset is doing a full scan of the data, whereas merge is just reading only the target columns that it needs, and executing the merge against those target columns. And actually, after the hash bucketing process, it dedupes things and it materializes things. It works in terms of record indices. So it usually doesn't ever even carry around the full record data from the columns it does pull. It just understands I need to keep the row at index 100, the row at index 500, so on and so forth. But yeah, there's a 3-step parallel process that I basically would call it a high-level hash bucket, dedupe, and materialize that it goes through, that I explain more in that presentation.
Brilliant. What is the frequency of data compaction? I mean, does this depend on at the time when the changelog has reached a certain terabyte or gigabyte file, and you want to do that, or you actually do that on a regular basis, or you can actually have data catalog programmatically on a nightly basis, do the compaction, and then recreate the indices and all that? How frequently you do the compaction?
So it's run asynchronously in practice right now in response to table loads being completed. So what happens right now is we'll load a table. The maximum frequency I think we typically allow table loads is once every 5 minutes for these large tables in particular. And so maybe once every 5 minutes, you may kick off this asynchronous compaction job, which will pick up the deltas and create this read optimized view. So yeah, in practice, I'd say least frequent is monthly. Those ones can get a little scary, actually. Most frequent is usually about once every 5 minutes.
And one final question, which product at AWS are you using DeltaCat?
Well, we actually don't necessarily use it inside of an AWS product right now. We're actually using it at Amazon kind of internally outside of the scope of AWS. So Amazon has an internal data catalog that it uses to keep track of, well, everything going on in the world of Amazon. And that's primarily where we're using it right now. So we're primarily focused on internal customers right now. But you know, AWS always keeps track of what customers want, of course. And so I'm sure if there's enough demand for having something like this and good Ray integration with AWS products, they will certainly be sensitive to hearing that and
well, lovely.
Seeing what they can do.
Well, thank you very much. I think we're just about 5 minutes over time. Patrick, Alex, Clark, Zhe, and everyone who was actually gave a talk today, including Robert. Thank you for answering the question both live as well as the questions on the Q&A typing in. We do thank you, all of you, for sharing your experiences with us. And we want to thank all the attendees who actually came up and attended and gave 2 hours of your dedicated time. Instead of having dinner with the family or having a pint at the pub, you're out there geeking yourselves. So we do appreciate that. We'll keep you posted on the video. We're going to share that with you. We're going to share all the questions answered in a separate document. We'll put that on the link. And then thanks a lot for coming, and stay tuned for more of these meetups in the coming months. We'll have more dedicated talks on the native libraries of Ray. And so stay tuned, and thanks a lot for joining us, and be safe. And we'll see you in a month or so. Cheers.